morning. Let's start. At first, let I introduce myself. My name is Julian Velchev. I'm assistant in the Technical University of Sofia. I'm a PhD. And our topic for today is fundamentals of signal processing. It will be something between signals and systems and digital signal processing. Maybe more signals and systems. And we have 4 subtopics. The first one is frequency analysis of signals. The second, in the second topic, we will discuss data conversions, analog to digital and digital to analog, some architectures and parameters of such converters. In the next we will talk about system analysis, continuous and discrete time, Laplace transform and Z transform, and the last one we will cover some basics of digital filters and a little bit of multi-rate signal processing. Here is my email, and my colleagues left here a list
for us to write ourselves.
Yes, because I see for yesterday. Excuse me, please, for this thing. I don't know how to hide this, because in presentation the resolution is not suitable for us. For this lecture, I will give you a short introduction, and we will talk about continuous time Fourier series. I think some of you are familiar with this. Also, let's continue in this mode. We will continue with continuous time Fourier transform, and we will talk about DFT, discrete Fourier transform. We won't cover discrete time Fourier transform and discrete time Fourier series. We will mention about them, although during during the lecture, I will show you some MATLAB demos for better clarification of the material. And let's start with what is a signal from informational point of view. This is some physical process that carries information. Our signal comes from sensors mainly, and our task is to process such signals and produce some an output signal. And our types of signals are one-dimensional, two-dimensional, multi-dimensional. We will discuss only 1D signal, but for multi-dimensional signals, the idea is the same. We will think for our 1D signals as a function of time, continuous or discrete. We denote a continuous time signal as x of t. Our variable t is the continuous time. For continuous time signals, here is an example. The values of our signal are defined for every time point. Opposite, discrete time signals are defined only for distinct time points. And we will call such signals sampled. The digital signals are a particular case of sampled signals. Every digital signal is sampled, but not every sampled signal is digital. We will discuss this in detail later. Here is the sampling interval, denoted by Ts, and we will use our n. N is the sample number index, 0, 1, 2, and so on. Other type of signals, periodic and aperiodic. Periodic signals are such signals that repeat in time. Aperiodic, of course, not. I have to mention the periodic signals are theoretical abstraction, because in real time we are going to see the periodic signal has to repeat, but this repetition must be forever. In real time we have limited duration signals, so in theory they are not periodic. Another two types of signals. Energy. Energy signal is such a signal that have finite energy, but its average power tends to 0. As example, thank you. Aperiodic signals are energy signals. the formula for the energy we integrate in interval from minus infinity to plus infinity, the square of the signal, and it should be less than infinity. Power signals are signals with finite average power, but their energy tends to infinity. As example, periodic signals are power signals, and we have signals that are not power, not energy. Energy for power signals is limited, but the average power is limited, but energy tends to infinity, because if we have
Дубките са били.
Okay, it's a good idea.
You need help?
Yeah, the horses are not aligned with.
Use the pencil.
One by one.
Maybe
So yeah, one by one.
can we use this? Is it?
Okay, let's try it with just one hole. Our periodic signals starts from minus infinity and continues up to infinity. If we square this and integrate from minus to plus infinity, obviously our energy will be infinity. Another two types of signals, deterministic and random. For the deterministic signals, we know everything. For random signals, we have some kind of uncertainty. From informational point of view, deterministic signals actually is not signals, because if we know everything, they don't carry any information, but we will call the deterministic functions also as signals. Up to here, we know our signals are a function of time. This is our common point of view. We can see a signal in oscilloscope, for example, but in some cases this representation is not enough informative for us. We want another point of view that can reveal some signal properties that can be not seen in its time representation. We want to represent our signal as a linear combination of so-called harmonic functions, sine, cosine, or complex exponentials. And such harmonics will be with different frequencies, of course magnitudes and phases, and from here to the end, of course, we will call this representation in frequency domain. Why we want such representation? The reasons are a lot, but the first one, we want to know which frequencies contribute significantly in our signal and which are not, and that's why if we want to transmit our signal through a communication channel, we will know the required bandwidth of the communication channel, because we want the signals to be transmitted without or with less distortions. And the second thing, we will discuss linear systems, and for linear systems, one thing is very important. Linear system do not change. Linear system only changes the magnitudes and initial phases of the harmonics that our signal is composed on, but retains the frequencies. A nonlinear signal introduces new harmonics that are not present in the input. We will discuss about so-called eigenfunction of a system, and it is a complex exponential function. So this is the second reason for this representation. And another, I think most of you are very familiar with analysis of electrical circuits, and you know how to analyze electrical circuit DC mode, Kirchhoff laws, and this circuit could be analyzed in AC mode, and we know how to analyze when the sine or cosine sources are present in the circuit, but when we have to analyze such thing for non-sinusoidal oscillation, we can make the composition of our signal, and we will have the representation as a sum of harmonics, and we are going to analyze the circuit for every harmonic, and we can use the principle of superposition and to guess what is going to happen if we have some kind of more complicated signal like this, for example. And using compression techniques, we can.
One question. So if we have like non-linear signal, which introduces change in the frequency domain as well, does that mean we cannot split it into the harmonics into the superposition?
A system, non-linear system introduces new harmonics. Almost every signal can be decomposed in frequency components.
What would be the situation where it cannot be done?
We can use some kind of approximation.
But physically, what can cause such behavior that cannot be decomposed?
We will talk about the Dirichlet conditions. If let's say we can have a signal with we'll give you an example. Imagine a signal that is periodic, and here is the period. Imagine the oscillations are increasing when the time tends to the period, and this frequency tends to infinity here when we approach this point. Such signal cannot be decomposed in, let's say in frequency series, because it has for this interval we don't have finite extrema, minimum and maximum, and in theory we can also represent this as Fourier series, but we can use some kind of approximation, and we will consider this maximum and minimums are not infinite. We can think about their finite. And we will have not exact representation, of course. This is mostly for continuous signals. For digital signals, actually, we don't have such a problem. And using compression techniques, Fourier transform are generally not used for this task, because as we will see, we will have complex numbers, and the calculation with complex numbers is not very convenient because of computational complexity. But such representation gives us the possibility to throw away some frequency components that are not very important for our signal. Our signal is decomposed in frequency components. Some of them contribute very significantly, some of them not. We can omit such insignificant components and we will compress our signal. The compression is losing. We will lose some kind of information here. In time domain it's not possible. I want a representation of this signal in frequency domain, let's say this. It has harmonics with amplitudes, and we have harmonics with very small amplitudes, and I will want to make a compression, and I will make something like this. I omit such components. The signal will not be the same, but almost. And I will retain the significant components. I can't do this in time domain.
So this is actually something good in everyday usage, right? Because we would basically, when we're decomposing the signal, let's say a speech, we're going to remove some that are not needed. We'll
Yes.
still get the main information that we need, and we'll save some space.
Of course, that's our idea.
Yeah, but when we're talking about like scientific implementation of grabbing data from the top, we don't want to lose any, right?
Of course.
So this would be something we're looking to minimize there.
Yes, we want to minimize the amount of
Data we use.
update. For example, for medical information, in some cases, this is not allowed at any. For some countries, this is for diagnostic information, such thing is not permitted. We are talking about continuous time Fourier series. We will consider a continuous time periodic signal, but let's start with such thing as orthogonal basis decomposition. This is some kind of generalization of Fourier series because we want to introduce the inner product. Here we denote the inner product with this way. It is an integral of the how to say in English, algebraic product of two functions or signals, u of t and v of t. We just multiply them and integrate them. But this integration is in limited interval from t1 to t2. We can't find orthogonality in unlimited interval. Now we have our inner product, and this quantity, in very simple words, tells us how u is similar to v. The result is scalar, and if this number is 0, we talk about orthogonality, U and V are orthogonal, and they are not similar to each other at all. Like you can imagine the situation with vectors here, if are they orthogonal. We don't have any projection of one vector to the second vector. We can express the first with the second or vice versa. And we are interested in this orthogonal signals because we will start to think about representation of our signal as a linear combination of such orthogonal functions. The number of these orthogonal functions is infinite, and they are mutually orthogonal to each other, and we will express our signal as a sum of our orthogonal functions, and in this equation we have coefficients. Let's say this is U1, this is U2, here is our signal x, and we want to find the projections, let's say C1 and C2. We can find these coefficients, and we will have an exact representation of our signals as such linear combination. So the important thing is that UI form a orthogonal basis in which we have zero inner product for any two orthogonal functions from this set, excepting in the case when I is equal to G. Now we have the inner product of one component by itself. Obviously, the inner product is not zero. We will have integral of the squared function, which is our energy for this component. And here we have the energy. We have now our orthogonal basis, and we will try to find these coefficients. The idea is the same. Fourier transform, wavelet transform, decomposition in Walsh functions. And a special situation when the energy is one, this is a particular case of orthogonal basis. We call this basis orthonormal. And we want to find the coefficients C. This is our expression. And the next thing is to integrate the both sides of this equation from time t1 to time t2. We know this coefficient can be moved on the integral, and we will have something similar. This is our inner product. I will show you again. But we know UI and UK. First, before integration, we multiplied both sides by UK. I forget about this, and we integrate. Now, the left side stays the same. The right side, in the right side we have inner product, but we know this inner product is 0 for any I not equal to k. But for I equal to k, this inner product is not 0. This is just the integral of squared element of our basis. And from this sum, only one term is not 0. And this is our possibility to express the coefficients. Let's say Ck is our coefficients, and it is just inner product of the signal with particular element from this orthogonal basis divided by the energy of this component. We have something very, very intuitive here. We have measure of similarity between signal and a particular component of our orthogonal basis. But we want just a similarity excluding the energy, so we normalize this thing by dividing the inner product to the energy. And in situation when we have orthonormal basis, the expression is simpler because we don't have because our denominator is just 1 and our coefficient is just a measure of similarity of x, and let's say this is our signal. We measure how similar is this signal to a given element of such set of orthogonal functions. And this equation combined with this one, we call them generalized Fourier series. Why generalized? Because we are not limited to harmonic functions like sine or cosine for u. U can be anything. We want just orthogonality. Sometimes the elements of our set of orthogonal functions are simpler in some sense than our signal. For example, such thing can be decomposed as a sum of sine or cosine components. We consider them simpler than our signal. And now we are ready to derive the continuous time Fourier series. We have our periodic signal x of t, and now we consider trigonometric functions for our set of orthogonal components. And instead of u of k, we will use sine of 0, sine of some kind of frequency, sine of 2 times such frequency, and cosine. There are many, they are infinite, and their frequencies are exact multiple, as you can see, 1, 2, 3, 4, and so on. And the interesting thing is that they are orthogonal to each other. if you take this and this, this and this, this and this, this and this, they are always orthogonal. If you, it can be checked very easy. Now we introduce our frequency 1 over t and our angular frequency. We call them fundamental frequencies, and t0 is fundamental period. As I mentioned, periodic signal is just a theoretical abstraction because in real world we don't have a signal that starts from infinity and continues up to infinity. But if you have repetition in the signal and its period is much less than signal duration, we may consider such signal as a periodic and apply the Fourier series. But if we have a situation like this, for example, only only three cycles. If we apply Fourier series for the spectrum of such signal, we will get very inaccurate result. And now, not every signal can be decomposed into Fourier series. We have just discussed this. Our signal has to satisfy three conditions, Dirichlet conditions. All this is the set of the strict Dirichlet conditions. Sometimes they think about the first two are the weak Dirichlet conditions, and our signal have to have a finite number of discontinuities in a period, and finite number of maxima and minima in a period. I just gave you such example with which contradicts to the second condition. But for first condition, that a signal that violates this condition is something like this staircase, and when we approach our period, the step is tend to infinity. We have here discontinuity, here, and the number of our discontinuities is finite, so it can be decomposed into Fourier series. For most real signals, we have satisfied conditions. And now, if we take inner product of sine n omega 0t and cosine n omega 0t, the result will be always 0. If we take inner product of sine with a frequency n omega 0t and another sine with frequency m omega 0, and m is different for n, this situation will give us a 0. So sine n omega 0t and sine m omega 0t when m is not n is always 0. Such thing is valid and for cosines we have orthogonality here, and if we recall if we recall our generalized Fourier series, we can just replace the coefficients and with we can just replace our orthogonal function with sines and cosine. Please excuse me. Here I denote the signal with s of t, but actually we used x of t as such notations. I didn't see this. And now we have coefficients a and b. A are for cosine, b are for sines, and we have our denominators, which are integrals of cosine, squared cosine and squared sine. This can be solved very easy, and the result is always half a period. Now, in our denominators we have half of period, and the final expression for such coefficients is this. For coefficients pk by analogy is the same, and we introduce a DC component. This is our zero frequency coefficient A0, which is nothing but the average of the signal in a period, DC component. And finally, we can express our Fourier series as a sum of DC components, cosine components, and sine components. Cosine components are even, sine components are odd. If we don't if we don't use infinity in our sum, but some k, which is not infinity, we don't have an exact representation. We have an approximation. But the interesting thing is that for any given k, the mean square error is always as small as possible. X cut is our approximate signal, x is our original signal. If I want to approximate a rectangular pose, the first component will be sine, and the mean square error is always minimal, because if we this area is equal to this area, and we will have overshot. If we take infinite number of sine and cosine, we have a perfect reconstruction. And another form of Fourier series is so-called polar form. Instead of sine and cosine, we just use cosine functions, but we have to introduce an initial phase, phi. This form is very clearly related to the previous one. our amplitudes are the square of the square root of the sum of squares of AK and BK small, and the initial phases are,
That's simply trigonometry, right?
of course. This is our BK, this is our AK, and this is our phase. Very, very simple. But this form is very useful for us because we have a very, very obvious physical meaning here. And we can now talk about what is the frequency spectrum. An example signal, periodic, it satisfies the Fourier and the Dirichlet conditions, and we can apply Fourier series on it. Such example is half-wave rectifier. And if we find the amplitudes and phases, we call this amplitude spectrum. A0, A capital 1, 2, 3, and up to infinity. And if we express the initial phases as a chart, this is our phase spectrum. Both are needed for exact signal representation. Several properties. This representation is linear, so we can apply the principle of superposition. If our signal can be expressed as sum of two, we can find Fourier coefficients as a sum of the Fourier coefficients of the other two signals. And obviously, if the area like here encloses equal. If we have equal area above and below the time axis, coefficients A0 will be 0. If the signal is odd function, it will contain only sines. All cosine components will be 0, and opposite. If the signal is even function, it will not contain any sine components, only cosine. If we translate our signal along the time axis, we change only the phase spectrum of EK. If we translate the signal along y-axis, phase spectrum of EK stays the same, but only the DC component A0 changes. The others stay the same. And maybe the most important property of the spectrum of periodic signals is this: if the signal is periodic, its spectrum is discrete. This we have samples at distinct frequency that are exact multiple of the signal component, signal frequency. We don't have anything here. If our signal is, let's say, 100 Hz with frequency 100 Hz. It will be decomposed into components with frequency 100, 200, 300, and nothing different, up to infinity. We will see that it is not true for aperiodic signals. This is property for only for periodic signal.
But if we have a finite signal,
It's not periodic.
it's not, but we can put batches of it on one after each other, make it periodic.
Yes, you can make it periodic, and if it is periodic, its spectrum will be discrete. I don't actually understand what is the
So we have some aperiodic signal, but it's finite,
okay.
and we want to decompose it.
Mhm.
If we have this signal, not in just this time frame, but like repeated continuously after each other, now it becomes periodic.
Yes, obviously.
So we can decompose it,
Yes, of course.
and we can get the representation in.
Yes. Yes, but if such replicas, when you add,
We're going to have a parasite frequency which is going to be equal to the finite time period, right?
you mean something like this. I have a signal, let's say, and I add more. But if the number is not infinity, it is not periodic.
True.
We can apply Fourier series and consider it as a periodic, but we will get a spectrum that is not the true one. I have some MATLAB demos that can clarify such situation. Another form of Fourier series, complex form. The idea is, I think, is obvious. Instead of amplitudes and initial phases, we can think about complex coefficients and so-called complex amplitudes. We can think about our coefficient is complex. Let's say Ck. Our real part is the cosine, is for the cosine components, and imaginary part is for sine components, and we have a concept for negative frequencies, because we have complex conjugation here. Ck coefficients is just a complex conjugate of the mirror in the negative frequency. Of course, just a mathematical abstraction, and we have now two-sided spectrum. If we combine sine and cosine, obviously we get complex exponential. Euler formula made this good idea to write for them. E to the j minus jx, let's say, is cosine x minus j sine x. Cosine x is e to the jx plus e to the minus jx over 2 x is
That's the same thing, it's just called in a different name, right? Every complex number can be presented
Of
as
course.
a sum of cosines and sines.
Yes, and obviously, instead of finding the similarity between our signal and cosine and sine, we just find the similarity between our signal and a particular complex exponential, and we will get a complex coefficient, ck. Now, our sum is not from 1 to infinity, but starts from minus infinity to plus infinity. And an example for two-sided spectrum, two important properties. The amplitude spectrum is even function, always. We have symmetry here around y-axis, and the phase spectrum is always opt. We have a central symmetry here. At this point. Do we need negative frequencies? We know by symmetry.
The first one is the amplitude spectrum.
Yes. And the second is the phase spectrum.
When would be a situation when it would be more convenient to use the exponent representation, the complex number, compared to the sum of sines and cosines? Or it's pretty much the same?
When you try to derive the continuous time Fourier transform, it's more convenient to use complex exponentials. Sometimes when you try to find the Fourier series, sometimes it's easy to use the complex form of the Fourier series because you have to solve just one integral. Nothing different. When we discuss about this, when we start to talk about discrete Fourier transform, we will see that representation is convenient. We will see that. And now I can show you some examples of signals with using MATLAB to show how they are decomposed into Fourier series, and we can see these properties that we just mentioned about. Is it the script clear, big enough? We have amplitude, our fundamental period, bias and phase shift are set to 0. Duty cycle is only for rectangular pulse train. K capital is the number of harmonics. I set them to 10. Of course, I can't make an exact Fourier series representation using PC because my computer doesn't know how to integrate. We can use a very small step, and we can use numerical integration. I use this here, and the step is very small. As you can see, much smaller than the period. We expect a good approximation. Here we have sawtooth waveform, amplitude over period times t, and obviously calculating of Fourier series coefficients should be placed into a cycle because only k is different for every term. And our amplitudes, our initial phases, the DC component, the DC term. The rest of this code is only plots. Here is the signal with blue. With red is its approximation with Fourier series from only 10 terms, sine and cosine. And you can see the amplitude and phase spectrum. If I take less harmonics, let's say 5, the approximation will be worse. If I want to take only 1, the closest thing for this signal is negative sign. If I increase them to 10 and maybe 100, let's see. Almost perfect. Actually,
It's actually worse in the peak values.
of course, I'm not able to compose such signal from sine and cosine with frequency up to infinity. I have only a finite set of sine and cosine.
But why when we increase the K, the value of the signal actually drop, like deviated further away? Or am I looking at this now?
Well, here
Yeah.
about such oscillations,
About the
0.5 level is here.
Yeah, but if you look at the maximum, there's like a peak there. Yeah,
Okay.
this is not good. If we reduce it to 10, we don't have that.
Maybe
But
Pretty much the same.
Pretty much the same. Our integration is not exact, and we can't reach discontinuity in time domain like this. We have discontinuity here with limited frequency. We can achieve it with frequency that tends to infinity. Infinity in frequency domain, discontinuity in time domain. Let's see another. If I try to decompose into Fourier series just a cosine, what do you expect? How many harmonics? Let's see. I think just only one. Because we decomposed an arbitrary periodic signal into sine and cosine. If we have just cosine, it is decomposed to itself. Just
Yeah,
one.
we took out the function, so yeah.
Huh?
We took out the function so.
These things here, ignore them. Because what is the meaning of initial phase if we don't have an amplitude? Our PC tries to divide 0 by 0, I think, and something weird. If I try to change the cosine with sine, the amplitude spectrum, my mistake, the amplitude spectrum stays the same. It is the same, but obviously we have a different phase spectrum, minus p over 2. This is our simplest signals, sine and cosine, so their Fourier series lead to just one harmonic, just one spectral component, and another signal may be rectangular. Here we have an interesting thing. Such a rectangular pulse train with duty cycle of 50% is decomposed only by odd harmonics, as you can see. The second, the fourth, the sixth, the eighth is zero. It depends by duty cycle. If I change the duty cycle to let's say 0.25, now not every second harmonic is 0, but every fourth. The fourth, the eighth, the 12th, and so on. If I try to set the duty cycle to 0.1, evident, but I want to show you something different. Do you see the envelope here? Can you guess about such function?
Looks like an amplitude modulation.
Yes, almost. I will show the envelope here.
It's probably some sort of sine times some exponent.
Uh,
Or
do you agree? This is something like this. The envelope. I show it in with negative frequency for if are you familiar with this sin x over x? If I take its absolute value, it is the same. Important property, we have a duality. If in time domain we have a rectangle, in frequency domain we expect sin x over x always. Another thing, I can just add bias. Our signal is translated by the factor of 3 to the y-axis. As you can see, the scale is a problem here. The values of these amplitudes stay the same. The new thing is our DC component, which is located at 0 frequency. Just the scale is not very. If I click here, it is 0.37, let's say. The same, just the scale is different. The amplitude spectrum starting from here up to infinity is the same, the phase spectrum is the same, the only thing that changes is the coefficient A0, which is our DC component. If I try to shift the signal by some amount, let's say 2, we measure this shift in radians. Our signal is now shifted. The amplitude spectrum stays the same. The phase spectrum is not the same. I think here are formula for coefficients calculating. As you can see, I use a library function called trapz. It is instead of integration. I don't have a possibility to make integration with PC, and we use numerical integration when we express our signals as a sum of trapezoids, and we can just find the area and some. If we choose enough small step, the result will be very accurate. excuse me, how did you proceed with our colleagues yesterday and the day before yesterday about the brakes?
We follow the program, but
Huh?
well, usually we follow the program, but it's however it's most convenient.
Okay.
It's
Um,
different each day.
If you feel like we're at the logical conclusion, we are starting something new,
Mhm.
maybe we can have like,
Okay. Let's continue. Up to 11. You are not tired.
not yet.
Let's continue with the average power. We want to know how each spectral contributes to this average power of our signal. The formula for average power is very clear. We have to integrate the square of our signal and average it dividing by the period. Now, instead of our signal here, we have its Fourier series representation, and we have to solve such thing. Our first term, our second term group, and our third term. The second one is 0. The second one is 0. Because why? Because we integrate cosine in limits in its period. If I integrate from 0 to t, I will see that two areas above and below are equal, so the result is 0. The third term, we know the result if we integrate the square of cosine, it is the half of period. A is a constant, so we get a very simple thing. We call it Percival equality, and it shows us how the power of our signal is distributed over frequencies. We can determine the average power in time domain just by integration and averaging of our signal in time domain, but we can get the same power in frequency domain if we apply this equality. The things are very simple. The average power is sum of powers of each harmonic the signal is decomposed on. Here is the power DC, and we have the amplitude square over 2, which is the power of a particular harmonic component. This can be solved very easy. We get this result, the square of the amplitude over 2. It's good to remember this result, the power of sine or cosine, the squared amplitude over 2. This equation gives us information where the signal power is concentrated on in frequency domain. Now, we have just finished with continuous time Fourier series. They are easy, and now we are start to talk about for aperiodic signals. Up to here, we know the a given periodic signal can be decomposed on sine and cosine components. But what about aperiodic signals? We can't apply Fourier series for them because we don't have a period.
Don't they say the period is infinity?
Yes. That's, we have such idea here. We have, let's say, an aperiodic signal, something like this. And how can we make it periodic? We cannot walk and say the period is here and it tends to infinity. And formally, our signal stays the same. We want to derive something from Fourier series for aperiodic signals, and we are starting with this assumption, and we can think about the following important things. For periodic signal, we have spectrum, which is discrete or sampled at frequencies 0, omega 0, 2, omega 0, and so on. The step in frequency domain is delta omega. We know omega 0 is 2 pi over the period, but if our period tends to infinity, yes, omega 0, which is the step, is very small. The frequency step tends to 0 when the period tends to infinity. Now we expect to have a continuous function, not sampled. When the period tends to infinity, we don't have a discrete spectrum, but we have some kind of continuous function of frequency. We will call this spectral density. Now, in Fourier series, we have k omega 0, but now it is meaningless to consider k1, 2, 3, and this thing transforms into a continuous variable omega. Now we expect a function of omega, so omega is now continuous. In our Fourier series, we had sum, because our step is too small. Obviously, we have to replace the sum with integration. We can transform. And in the common case, we want to integrate from minus infinity to infinity. We don't have a period here, actually. We should work with infinities. Now, 2 over t0, when we consider such transforms, tend to d omega over pi, and now we are going to use the complex form of Fourier series. Let I show it again. Now we have some for our situation. This sum will be transformed into integral. Here k omega 0 will be our continuous frequency. This 2 over t0 will be d omega over pi, and what else? Our coefficient. Here we have coefficients C1, C2, C3, but in the case when the frequency is now continuous, we expect to have a very small growth for this coefficient. We denote this growth as DC, very small. Now, we can just use the formula for the coefficient. The term 2 over t0 is replaced with d omega over pi. We integrate from minus to plus infinity, not in period. We have our signal. Instead of j k omega 0, we just have j omega. And now, if this coefficient is replaced here, I will show again. We put this coefficient, this formula here, and this summation is transforms into integral. Now we have so-called double Fourier integral, and with some simple arrangements, and we can express the result, the inner integral here. Can be seen here, and as you can see, we have as a result a function that is function not on time but frequency. T variable, time, drops. We don't have a representation in time domain anymore. We have a representation on frequency domain. What is the physical meaning of this? We can express such complex function as is magnitude and angle. The magnitude will be our amplitude spectrum, and the angle will be our phase spectrum, by analogy with Fourier series. Now, we are ready to formulate the continuous time Fourier transform. We denote such transform with F. This is the forward transform, this is the inverse transform. What is the interesting thing here? We have to integrate the product of a signal and complex exponentials. How many complex exponentials do we have? How do you think? Infinity. How do you think? Are they orthogonal to each other? As in Fourier series? No, they are not anymore orthogonal. Some of you are familiar maybe with wavelet transforms. Two types, continuous and discrete. In discrete versions, they are orthogonal, but in continuous version, they are not. No orthogonality. Here we have the same thing. If we apply what this transformation gives to us, just a function that is a similarity of the signal and such complex exponentials. And we get a signal in frequency domain, and if we apply the inverse Fourier here, note we integrate now not in respect to time but in respect to frequency. So we integrate our spectral density with respect to frequency. So the frequency drops, and now we have time. We have perfect reconstruction. We have signal, its spectrum, from spectrum back to signal. We don't lose anything. Of course, unambiguous and invertible transform from frequency to time domain back. And this is our magnitude spectrum. Always even function if the signal is real, not complex. We consider real signals, so we expect to see double-sided spectrum, which is symmetrical in respect to the y-axis. Phase spectrum, which is the angle, always odd function. By us, we have talked about the Dirichlet conditions. We have something similar. Not every signal can be transformed using continuous time Fourier transform. We have the following condition. It means that this can be done on a signal on signals with finite energy. If the energy tends to infinity, it cannot be performed. Not directly. I will show you how to make such thing.
Then probably, like you showed the function where it's in frequencies going towards infinity at certain points, maybe we can integrate the lambda. Kind of, and not go into the singularity point where so not from minus infinity to plus infinity, but just skip the part where it.
Of course. Yes. And I will show you how can we make a workaround for such a signals that do not that have in energy tends to infinity. Now, some properties of Fourier transform. It is a linear transform. If you have to find the spectrum of a signal that can be a sum of other signals, you can just find the Fourier transform of each signal and sum the spectrums. The principle of superposition stands here. The second thing, if you want to find the Fourier transform of time-shifted signal, how do you think? Which term is changing? Changes the amplitude or phase? Just phase spectrum. The magnitude spectrum stays the same. If we shift in time domain, it is equivalent in frequency domain to multiply by a complex exponential a to the minus j omega the delay tau. Now, time scaling. If we have a signal in time domain, in frequency domain, maybe it will be something like this. Sine x over x or sinc function. Now, if I try to stretch or make it short, my mistake, it's here, not here. If I try to make this pulse short, in frequency domain, the following thing. When I shrink in time domain, the things in frequency domain are extending.
We add more uncertainty, right?
Yes, we have to,
Measure a smaller signal.
if we try to transmit such signal over a communication channel, the channel should be with very high bandwidth. Now, the second, the next derivative. If you want to find the Fourier transform of a different derivative of a signal, it is just to find the Fourier transform of the original signals, and finally we just multiply this by j omega. This means the differentiation tolerates high frequency and suppresses low frequencies. Do you agree? We just multiply by omega. For large omega, this is large. The integration is the opposite. If we try to find the Fourier transform of an integrated signal, we have to find the Fourier transform of the original signal and divide by j omega, which means integration is equal to suppress the higher frequency.
So like a filter.
But of course, low pass filter. Something like integration will be something like this. Not very ideal, but yes. Now, the next property. We want to find the spectrum of a signal that is multiplied by harmonic function cosine omega 0. We call this property modulation property. It's very interesting and important, I think. What does it mean? Let I suppose I have a spectrum.
That's frequency modulation, though.
Amplitude. Yes.
Oh, yes, amplitude. I think yes.
Let's suppose we have spectral density like this. Let's make the things simpler. Let's consider that our spectral density is real. Can we? Why not? Here are our negative frequencies. Let's suppose this level is 1. If I multiply this times cosine omega 0t, and what is the result? Using this formula, this thing splits into two parts. And the first part is here around frequency omega 0. The second part is around frequency minus omega 0. The level here will be the half, splitting the spectrum just by multiplication of cosine. Is this modulation? Of course. Now we don't have spectrum in lower frequency, but in higher. Amplitude modulation without carrier in the spectrum in frequency domain. That's modulation property. And another modulation property, if we multiply by sine, the things are similar. Here is the shifting, splitting and shifting. By Euler's formula, we can express a complex exponential with sine and cosine term, and if we multiply a signal by a complex exponential, the result is that the spectrum is now shifted in frequency domain. If I have some kind of spectrum, if I multiply by, let's say, J, these things shift to the new frequency. Two more properties: multiplication, Fourier transform of product of two signals, and if we multiply two signals in time domain, the result in frequency domain will be convolution. Are you familiar with convolution? Okay. And we will talk about convolution. If we try to find Fourier, continuous time Fourier transform of a convolution result of two signals, these things is just a multiplication on a frequency, in frequency domain. Important properties, because we always prefer multiplication instead of convolution. We can just do this in another domain, in frequency domain. Some examples. Let's try to find the spectrum of a rectangular pulse. Like this. This signal is somehow weird. As you'll notice, it starts from negative time. It's not the real thing, of course, no. But it's easy to be solved. That's why I have chosen such a signal, but it's no problem to find the Fourier transform of something more real, like this. Can I find the spectrum of this signal and apply the shifting property? Of course. Now, we have defined our function in time domain. We perform Fourier transform. Our integration are in these limits where the signal is not zero, and we have this result. We have just written the Euler's identities, so I can multiply by 2 and divide by 2 to get one of the Euler identities, and we have our final result. It's not very obvious, but I can multiply by TP, divide by T, I multiply by TP. Now, do you agree that we have a function of type sin x over x now? It is that's better, maybe. Sin x over x and a scaling factor. As you probably know, the limit of such sin x over x when x tends to 0 is 1. This thing is 1. We get sin x over x in frequency domain, but we can see the following. This function crosses the omega axis in the frequency 2 pi by the pulse width, 4 pi divided by the pulse width, and so on. Obviously, when we shrink the pulse, the spectrum is extended. This level here, it's equal to the area of our pulse, 8 times the pulse width. The next important signal is Dirac delta. This thing doesn't exist in real world, but it is important for us because it reveals most of the theory in signals and systems. This pulse is 0 except when time is 0. It is 0. Now when t is 0, the amplitude tends to infinity, and when time is not 0, it is back to 0. Like this. Infinity and 0. And the most strange thing is that very tight and very high has an area of 1 of unity area. Nobody can imagine this, but area is unity. You can think of for delta as a rectangular pulse with unit area with pulse width that tends to 0. Now we want to find the Fourier transform for its spectrum. We just apply for Fourier transform, and the things are very easy here because we have to multiply two terms, but the first one is not 0 only at t is equal to 0. So we can substitute t just by 0, and we have the integral of our delta, which is nothing but its area. We know the area. Area is 1. We are ready. For delta function, the spectrum is real and flat with value of 1. This area of 1 corresponds to this level of 1. We had a rectangular pose, and here is the area. If I make this width, this width tends to 0, this point will be in infinity. Just a limit of rectangular pose. Now, up to here, we know we can apply Fourier transform on periodic signals, but can we do this on periodic? Not, because periodic signals doesn't satisfy this condition. If our periodic signal starts from infinity and continues up to infinity, its energy is not limited. So we can't. But we can do this indirectly. We know a periodic signal can be expressed in its Fourier series. Can we express it in Fourier series? Yes, we can. Can we perform Fourier transform with its Fourier series? Why not? Now, we want to find an inverse Fourier transform of delta in frequency domain. This delta is the same as this, but not as a function of time, but as a function of frequency. We want to know which signals do we have in time domain with spectrum delta in frequency domain. We can just apply Fourier transform, inverse Fourier transform on delta. We can just substitute omega with 0, and final result is 1 over 2 pi. Now, let's find the spectrum of this delta in frequency domain, but when it is shifted by some amount of frequency omega 0, we can apply the shifting property, and the result is here. Now, we now have another transformed pair. If we have in time domain e to the j omega 0 t, in frequency domain we have Dirac delta, scaled by a factor of 2 pi and shifted, but still Dirac delta. Now, what is the result if we apply Fourier transform on periodic signals? Up to here, we know our spectrum with Fourier series is one half C1, C2, and so on. This is with Fourier series. If we use Fourier transform instead of samples, we will have Dirac doses. The area here will be times 2 pi, delta. So, by the coefficient ck. So, this area is just pi by C2. Just with Fourier series we get samples, with Fourier transform we get Dirac process. As we saw that for periodic signals, the average power can be found in frequency domain also. Of course, it is the same as that is found in time domain. For periodic signals, we have a similar thing. We can find the energy of our signal just by integrating its energy spectrum, which is nothing but the square of the spectral density. If we square the spectral density and integrate it, we will get the energy. Squaring of complex function means multiplication by its complex conjugated, so we get real function, of course. And we have something similar for Perceval identity for periodic signal. We have for aperiodic, the energy is found in time domain and the same is found in frequency domain. Now let's have a break.